Let's implement the read method. So I'm going to activate this code block. First of all, we'll keep this statement read requested, and after that the current file position, and after that we have to adjust the count. So you have to compare with maximum device size. You have to get maximum mem size of the current device. In the open method, you already saved the device private data in the file pointer. You can extract that from this pointer. Let's do that. Let's create one structure variable for our device private data. PC dev data is equal to, so you can extract it from file pointer private data. This is actually a void pointer, that's why you have to typecast here. Struct PC dev private data stop. So int max size is equal to, now you can use this pointer PC dev data to extract the size information. Now we can use this max size variable here. If this current file position plus count is greater than max size, I'm going to remove this max size, then count is equal to max size minus the current file position, and after that copy to user. In the copy to user, the first argument is always the destination. This is read, so destination will be user, so buff, that's correct. And this should be the device buffer. How do you get the device buffer? You have to point to the device buffer. So we can get that from our device private data structure, pcdev underscore data. Dereference that, and let's point to the buffer address, plus you have to add the current file position, star of f underscore position. I think this is fine. After that you have to update the current file position here, that's fine. Number of bytes successfully read, updated file position, and return number of bytes which have been successfully read. That completes our read method. Let's quit and let's try to build it. No problem with the code. Let's complete write method. The same thing, you should need this information, that is private data information, and this max size. So I'm going to copy these two lines, and I go to write method. Let's paste here. So let's get rid of this if 0. Again, I'm going to extract the private data. So write requested for these two will remain, no problem. So here it should be max size, and here replace this with max size. Max size, this will be max size count. So copy from user. Now the destination is our device buffer, that's why we have to change this first argument here. PC dev data buffer plus the file position, and after that everything will be as it is, no problem. So we successfully completed our write method as well. And now let's quickly test it. The build is fine. Let's implement the elseif method as well. Again, I'm going to copy these two lines, and I'm going to paste here. I'm going to create one temp variable, elseif requested current value of the file position, that's okay. This is once information offset. Here just replace this with max size and offset. So offset is given from this method itself. You are updating the file position. Everywhere change this dev mem size with the max size. Let's go to the release method. In the release method we have got nothing to do, so that's why just return 0. That completes our exercise, and let's test this in the next lecture, and after that let me come back to this check permission. I'll see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let's include a check permission functionality to our driver. First of all, whenever the user application tries to open your device file, it actually uses open system call. If you just closely observe this open system call, you can see that there is a field to indicate flags. What are these flags? These flags could be, as this man page says here, the argument flags must include one of the following access modes. That means the user application is going to indicate the access modes in the flags field. The access modes could be read only, write only, or read write. When this system call is issued, your driver's open method gets called, and this access mode is supplied to your open method through the file pointer. That means if you check the struct file data structure, because as you know that your driver's open method gets a pointer to this struct file kernel object. Here is a field f_mode, f_mode. So this access mode is actually stored in the field f_mode in the struct file kernel object. That means in your driver's open method, you should check this field. Let's understand how to decode this field. Remember that this is one of the fields of struct file defined in Linux fs.h. You can check this field in your driver to understand access mode requested from the user space application. f_mode has bit fields to indicate access modes read or write. In order to decode that bit fields, you have to use these macros, fmode read and fmode write. These macros are actually defined here. You can search for that, fmode write. Here it is. You have to use these macros, fmode read and fmode write. Now let's see how to decode this field. Suppose, so in your driver, you access the file pointer and then you get the fmode field. You have to do a bitwise AND here. If you do bitwise AND with this macro, then if it is true, if the result is true, then that means file is open for just read or read write. This macro checks whether the read bit is set or not in this access mode field. And similarly, if you do this, if you use the macro write, and if you do bitwise AND operation with this value, then if this is true, then the file is open for just write or read write. If you want to check exclusively for read only, then you should be doing something like this. First check whether it is open for read. If this is true, and you have to use here logical and it shouldn't be opened for write. That's why this field must be false. So if this is false and the negation of false becomes true, then only you can conclude that the file is open for read only. I hope you get this logic. Okay, the same logic we are going to use in our check permission function. Let's get back to our editor and let's start coding. Now let's implement this check permission. For this function, I'm going to pass two arguments. One is device permission field, so that I can get by PCDev data perm field. And after that, I'm going to pass another argument, that is the fmod field of the file pointer. Let's go to the check permission, which is right here, and let's create some receiving variables. I call it as dev perm, and I would call it as mode or access mode or something. Access mode. What are our device permissions? Read only, write only, and read write. Let's create some macros to define that. Hash define, let me create one macro, read only, and the value is 0x01. These are just assumed values. You can give whatever you want. Write only 0x10, and hash define read write 0x11. Let me cut this code and I would paste here. Basically, we would have created these macros when we initialized this structure. Here in the permission field, let's use those macros. Read only, this is write only, and this is read write. Let's get back to the function. First, you have to check if the device permission is, if it is read write, then you need not to check the access mode, just return 0. If device perm is equal to read only, then you have to check the access mode. Let me write like this: if dev perm is equal to read only and logical and, so you have to use the access mode, decode it, decode with fmod read. If this is true, and you have to use one more logical and, the write bit field should be 0. You should confirm that because this is only for read only. And access mode, check for write field, fmod write. This becomes a complex comparison, so let's do one thing. Let's put this in a separate parenthesis. This is a separate parenthesis and this is a separate parenthesis. Let me explain once again. If device perm is equal to read only, and if the file is open for read, and if the file is not open for write, that you should confirm. That's why I should use negation. So if the file is not open for write, then negation of that would become true. Then we can confirm that this is a read-only access. If this whole statement is true, then you just return 0. And similarly, you have to do it for write only. Let me copy these two. Let's do for write only. If the device permission is write only and access mode, compare with write and make sure that it is not open for read. So this ensures read only access. Otherwise, just return -e perm. This would be our check permission function, and with this change we are ready to test now. First of all, let's confirm whether this builds or not. This builds, no problem. Complete up to here, and in the next lecture let's test it. I'll see you in the next lecture. Let's test our driver. Now let's first build the project. Just run make host. So now let's test this exercise on host itself. Use insmod to load the driver. Let's check the dmessage. You can see that the driver init was successful, and it has created 4 device files, and these are the device numbers. Let's check those device files. Here you can see that in the dev directory 4 device files have been created. Now let's try to write some data to PCDev1. Let's do that. Echo, I'm going to write some data to PCDev1. Here it is. It says operation not permitted because our driver has returned the negative error code, that is -EPERM. You can check the dmessage here. So you can see that the minor access was 0. This is a minor 0, minor 1, minor 2, minor 3. Remember that. Minor access was 0, open was unsuccessful. So we'll use strace with dd command. dd input file is equal to, by the way, if you want to know what is dd, just type man dd convert and copy a file. You can use this command for read and write. I'm going to use strace dd input file is equal to any file, any text file or anything you can take. Let me take our .c file, and output file is the device PCDev1. Let's try to run this code. So it takes some data from this file, that's the input file, and it tries to write into the output file. The output file is our device. Now let's run this, and you can see that strace prints all the activities which are involved in executing this dd command. All these system calls are involved in executing this command. Somewhere you see there is an open attempt. You can see that here there is an open attempt. The program tried to open the PCDev1 with write only and with these access modes, and our driver detected this write only. That's why our driver returned this error code, EPERM. You can use this strace command to debug your user level application. Let's do one more testing. What happens if let me remove this strace. So what happens if I use this command on PCDev2? Will it be successful? Yes, it will be successful because this command will open this file for read only, and this command would open this file for write only. Write from here to here. Let's see what happens. This command looks partially successful because while writing to PCDev2, the device memory was full, and that's why our driver would have returned no mem error code. Let's check the message. So you can see that minor access was 1. This is minor 1. Open was successful. Write requested for 512 bytes. That means dd by default requests for 512 bytes. That's a block size of the dd command. You can change that block size using bs argument, but you should just know that dd always tries to read or write 512 bytes at a time. That's why write requested for 512 bytes. Current file position was 0 in our driver. Number of bytes successfully written. Yes, it successfully written is 512, and after that the dd command again requested for 512 bytes. You can see that the dd command again requested for 512 bytes. But our device was already full because the maximum mem size of PCDev2 is 512 bytes. So that's why our driver printed here no space left on the device, and it returned no mem error code back to the user space. So that's why the dd command printed here cannot allocate memory. That means there was a partial copy. Let's restrict dd command to request for data only one time. You can do that by using count argument. Just give count is equal to 1. Here you can see that now there is no error. Let's check the dmessage. So here you can see that open was successful, write requested for 512 bytes, and it requested for only one time. Let's try to read from dev2. So let me change the input file as dev2, the output file as some file.txt. Let's hit enter, And here you can see that it says that operation is not permitted because PCDEV2 is write only. You cannot read it. Now let's run this code one more time. But in this case, instead of PCDEV2, let me use PCDEV3. And you can use count is equal to 1. And you can also restrict the block size using BS command. By default, the block size is 512 bytes. Let's restrict to 100 bytes. 100 bytes will be read from this file and it will be returned to this file. And it will be done only for one time. And the block size is 100. Let's try. 100 bytes copied. So let's check the dmessage, what it says. So the minor access was 2. This is minor 2. And open was successful. Write requested for 100 bytes. Because BS is equal to 100. Current file position is 0. Write was successful and everything was successful. Now you can do cat. You can use the cat command to read the dev3. Hit enter and you can see that it is actually printing some data. You can see that read requested for these many number of bytes, because cat always requests for these many number of bytes, but the number of bytes successfully read is 1024. And you can see that again cat request for these many number of bytes, but our driver actually says nothing to read. That's why cat gives up and it releases the file. And try with more commands like copy, cat, echo, dd to play with these device files. You can also use copy command to copy from one device file to another device file. In the next lecture, let's do one more testing. So let's write a simple application, a Linux application involving open, read, lseek system calls, and we'll again test our driver. I'll see you in the next lecture. So in this lecture, at the resource section, I have attached one file. Please download that and just open it. I'm going to explain that program now. The file name is dev_read.c. This is a very simple program to open and read data from the device file. Let me explain this program. So there is a buffer here, the global buffer, where I'm going to keep the data, whatever I'm going to read from the device. Let me just explain what this program does. First of all, I actually open a device file here. In this case, I select PCDEV3. You can take this device file information through command line itself, but for this exercise, I just hard-coded it. You can implement the command line version. I'm going to open this device file with read-only access mode. So this does the error checking here. If open returns negative value, then the open is failed and the appropriate user space errno variable will be set. You can use this perror API to decode that errno value and print the meaning of that. If the open is failure, then I just go to the end and I execute closefd and I just return. So please note that many people argue that using goto is bad in programming. That is true, but it is okay if it's a straight jump and if it is simple. In kernel module development, the goto is used if it is a straight jump, and it is very helpful in error handling. And after that, it prints open was successful here, and this is a block where it does reading. We are going to attempt reading twice. Here is a read API. Let's just explore this read. Read from file descriptor, and it takes these three arguments, the fd, which you got from open, and this is a place to give your user buffer pointer, and this is how many bytes you want to read. Remember that on success, this read can return either 0 or a positive value. On success, the number of bytes read is returned. If it is 0, then that indicates end of file, and the file position is advanced by this number. It is not an error if this number is smaller than the number of bytes requested. This may happen, for example, because fewer bytes are actually available right now. The read system call may also return negative value. If it is negative value, then that could be because of these reasons. So read returns 0 or a positive value or a negative value. That's why I'm checking for all those conditions. If it is 0, then I just print this is end of file and I just break this loop. And if return is negative, then something went wrong. I just break. If the return is positive, then this block will get executed. Let's see how we use read here. First of all, I give FD here and the buffer address. This buffer is traced by this variable total read. So this total read is initially 0. That means we start from the beginning. This variable actually holds count of total number of data bytes read so far. Initially it is 0. And the remaining variable holds remaining data bytes to be read. Initially it is initialized to this value. It is now 10. That means this program wants to read 10 bytes of data. That's why remaining is initially set to 10. So the remaining is used as a count here. Let's say you execute the system call and it returns 5. So let's say 5 is less than remaining. That's why the total read is incremented by 5. Remaining is decremented by 5. And this logic again tries to read one more time. That's why n is not equal to 2 and remaining shouldn't be 0. If remaining becomes 0, then there is nothing to read. This while loop breaks. So I hope you get this. So it tries to read one more time like that, and after that it just dumps the buffer here. Let's try this. Download this code and just compile that with GCC -o. Let me give the name devread. Before testing this, let me use the echo command to put some data into the PC dev 3. I'm going here and I copy some data, I paste here, and let's put this in dev PC dev 3. Let's do dmessage. You can see that we wrote actually 479 bytes. Let's execute dev read. So you can see that we actually read 10 bytes of data. So our application read 10 bytes of data from this device file. So now let's edit this code to get the read count via the command line. Let's make use of the command line arguments. So that's why let's edit this main arguments as int argc, and the second argument is argv. Here let's just test if argc is not is equal to 2, then let's conclude that it's a wrong usage. Printf wrong usage. Usage is you have to execute the file with read count. So go to out. That means you have to execute this program with a read count value. And now let's extract the read count from this argv pointer variable. Basically it contains a string data. The argv actually contains the string data. That's why we have to use a to I, ASCII to integer of argv1. Remaining is equal to. Let me just print the initial value of remaining. For this A2I standard library call, you have to include stdlib.h. Let's include that. Let's compile and let's execute. So here it is, it's a wrong usage. Let's execute with 10. Read requested is 10. Open was successful. Read 10 bytes of data. This is the data. Let's request for 10,000 bytes. And here it is. Read requested 10,000 bytes. But the first read actually got only 1024 bytes because our device has limitations. And that's why our program again tried for reading some data, but it got 0. It printed end of file. That's why the total read was 1024 and this was the data. Check the D message. Here you can see that the open was successful and our application requested for 10,000 bytes. But the successfully read data was 1024 and you can see that our application again requested for 8,976 bytes. That was read executing for the second time. Since there is nothing to read from the device, our driver just returned 0. That's the reason why our application printed here end of file. Then our application closed the file. So the release was successful. I have attached this application with this lecture. Try to download it and test your driver, what you have written, and let me know if you have any questions. I'll see you in the next lecture. Now let's test our lseek method. For that, just type man lseek to understand how to use lseek. So lseek takes 3 arguments. You already know this. The first one is the FD, that's the file descriptor, and the offset and the whence information. The whence information could be anything: seek set, seek cursor, or seek end. Suppose if it is seek end, let's say the file offset is set to the size of the file plus offset bytes. Here you have to mention how many bytes you want to seek with reference to this whence information. Let's try this. Let's go to our application and activate this code block. Activate this for lseek testing. So let's try to seek for 10 positions, let's say, from the end. And from the end, the file position tries to go to 10 position further. That is not allowed for our device because our device has some limitation. It has got fixed memory. So once you reach the end of the memory, you cannot seek further. That's the end. That's why I think I would expect our driver to return error code here. If this fails, then there is a problem. So if return is less than 0, lseek out. Here out you can do close FD here. Close FD target you can give. I would give close FD here. You have to close FD first, then return. Let's try this. Before testing, remember that, so we have to initialize our driver's lseek method in the file operation structure of our driver. That's why open your driver source code, go to the file operation structure, and you have to initialize the function pointer for the lseek member element of this structure. Dot double lseek is equal to pcd lseek. This you have to include. And after that, unload the driver, build the project once again, and then load back. And now let's compile our application and let's execute. Here you can see that the open was successful, but the lseek failed. That's an invalid argument because you're trying to seek 10 positions further from the device end. That's not allowed for our driver. I mean, this is entirely driver dependent. It depends on you how you code your driver. So now let's change our application. And let's do something else here. Seek set. So you can do seek set. Let's see what happens. There is no data in the device actually. Let's put some data. And now let's try to do this. So you can see that the position was first moved to 10 bytes away from the beginning. This is the output. So now you can see that the output is not from the beginning of this line. Output is actually at the offset of 10. This is the offset of 10. That's why first the file position is adjusted to the offset which we mentioned, that is 10 offsets, and from that it printed the data. What if I give -10 here? Let's see whether it takes that condition or not. So that's an invalid argument. I think our driver checks that. Try with different combinations of user level system calls, and with that note I would like to end this lecture here, and let me know if you have any questions. I'll see you in the next lecture. So in this lecture, let's understand the container of macro by creating our own container of macro. If you have understood how it works, then no problem, you can skip this lecture. Basically, we are understanding something from scratch. First of all, let's say you have a structure. This is a structure definition, and here I have a structure variable data, and there's a function called init where I have initialized all the member elements of this structure variable. After that, here is a function call, and here I'm passing the address of one of the member element. For example, C is a member element. I'm passing the address of that member element. Here, remember that C is a member. So who is a container of C? That is data. Data is a container, remember. This is a member. This is container. Once I pass that address to some other function, this function may be defined in some other file, let's say. So the address will be received at this variable. What you have to do is, using this pointer, you have to get back the address of its container. Who is its container? This one, right? That is the task. For that purpose, we actually use the macro container of this pointer. At this pointer holds the address of one of its member. The member is C. What you have to do is, you just have to first pass the pointer, so address of the member element. The member element in this case is C, and this should be the structure type. The structure type is struct some data, and the third argument should be the member name to which this PTR refers to. Member name is C. If you give this much information, then container of macro will calculate the container's address, and it will give you the container address. Fair enough. Now let's do one exercise. Now let's create our own version of container of macro. Here I have a small program, so I just use the online tool to write some code. Here is a struct, and this is a variable, and this is a main where I initialize everything. I pass the address of the member element C to this function. By using the PTR, get the address of its container. Here you should be doing some manipulation over the structure and its various addresses of the member elements. To do this exercise, you first understand the memory plot of this variable, how the memory plot of this variable looks like. Here is a memory plot of struct variable data. Data has 4 variables. The first 4 bytes will be consumed for this variable char. This gray area is actually padding. Basically, the char A actually consumes 4 bytes here, and int B consumes next 4 bytes. Char C consumes next 4 bytes. Actually, it consumes only 1 byte. Rest are for padding, because as you may be knowing, in an unpacked structure, the variable will always occupy the natural size boundary. That's why it looks something like this. collectively this structure actually consumes 12 bytes. Let's say its address is 0 cross 100. 0 cross 100 also happens to be the address of the first member element, that is A, which we can also call it as a container address. And this is B, which comes at 0 cross 104. This is the address of the member element B. Likewise, this is the address of the member element C, and this is a member element D's address. So now you have this address, isn't it? You want to calculate its container address. The container address is 100. How do you calculate? So you know this address. You take that. Let's keep it as X. You have to subtract something. What you will be subtracting is this variable's offset from the beginning. How many offset away this C is from the beginning, you have to calculate. 4 plus 4, right? 8. All you need to do is X minus 8. X is 108. So 108 minus 8 will give you the value of this container. That's what container of macro does. That's it. Now let's see how to deduce that using some piece of code. First of all, we have this address, isn't it? All we need to do now is we have to calculate member C's offset from the beginning. That's it. And just subtract that from the address. You get the container's address. Let me create one variable to store the offset. Offset. So offset is equal to, how do you calculate the offset? So to calculate the offset, I just create one temporary variable of this struct some data temp or something like that. And now what I do is I take the address of the member element in which I'm interested. That's why by taking the member element C's address, we have to deduce the container's address. That's why I have to calculate the offset between the member element C and the beginning. That's why what I do is I first take the address of the member element in which I am interested minus beginning. Beginning is temp.a. I would typecast this to casta. Let's make it everything casta. This gives me one quantity, a value. Basically, this will be a pointer type. This result will be of pointer type. I have to convert that into a value. Let me just typecast that into int. Now I got the offset here. For example, if this address is 108 and this address is 100, then 108 minus 100, so 8 will be stored here. That's the offset. And then I have to subtract this offset value from this pointer. That's it. I would create another variable to store the container's address, struct some data. Let me create a variable. Let's say data1 is equal to this ptr minus this offset. So I have to typecast. This is a pointer arithmetic. This will result in pointer quantity. That's why I have to typecast this to struct some data stop. Now you got the container's address here. That means the address which is same as its base address. So this variable's base address. Let's print all these details using this pointer. That's it. Now let's run this code. Let's see what happens. You can see that by using this pointer, you are successful in printing the details of this container variable 105A100. But here I have used one extra variable. Actually, using this extra variable is not required. You can use something called as zero dereferencing. Here what we did was we calculated this difference by taking this local variable's address as a reference. Instead of that, you can remove this and you can take 0 as a reference. What I do here is So I will remove this. First of all, I will take 0 as a reference, and I will typecast this 0 to struct some data star. Now I converted this 0 into a pointer of this type, and I select the member element in which I'm interested, C. And here you should be careful. You have to put one more parenthesis here, like this. You took 0 as a reference, and this is not a dereferencing, remember. So you are not dereferencing and you are reading the value of C, something like that. It's not like that. If you try to do that, then there could be a segmentation fault. Here we are just evaluating the address of the C with respect to the reference 0. That's why you have to use an ampersand here. This is not a dereferencing operation, remember that. Some of you may be having doubt that this would lead in segmentation fault. This won't lead to segmentation fault. So if you remove this, then this would lead to segmentation fault, because it's like reading the value of C by dereferencing 0. But if you give ampersand here, the compiler will generate the instructions to calculate C's address with respect to this as a base, 0 as a base. Now here we get the address of C, isn't it? We have to subtract the address of the beginning, but beginning is 0 in our case. Why? Because we took 0 as a reference. That's why if you take the beginning, then that would become redundant. So that's why you need not to subtract here. So now let's run this code, and you can see that you get the same result. You get the values of the container. So it actually shows one warning here. That's because the compiler is saying to consider this as a long. So you can consider this as a long. Let's try this. If you want to get the container address by using the variable, let's say B, then you have to pass B here, and here you have to change this variable. That's the reason why container of takes member name. You have to modify this to B, and then everything will be same. Here it says the incompatible one, because you have to typecast this to char star, because the receiving is char star. B is actually of integer, right? How to make this as a generic macro? It's a C function. Now let's convert this into a macro. Let's write our own container of macro. Define container of, so you would need a pointer, and you need a member name and a struct type to typecast. That's the reason you have to take struct type and member name. So the final output of this macro should be a pointer of this type. Let me write that first. Type star. It should be a type star. Here you should be doing this one, ptr minus offset. Ptr minus offset. Offset, this is how we calculate the offset. You have to take the 0 as a base, dereference member. This 0 has to be typecasted. Let's typecast to type star. That's great. Now keep this quantity in another parenthesis, and you need its address. So ampersand, pointer minus this quantity. Both should be of same data type. That's why let's convert them into a char star data type, char star, and this quantity as well. Convert that into a char star. This is the first quantity and this is the second quantity. And the result will be typecasted to type star. That looks good. Now put everything in another parenthesis. So now we can remove all these things. Let me disable this code block. And let's get the container address at this variable using our container of macro. Container of ptr struct type struct some data. Instead of doing this here, I would cut this code and I would do that here itself. This function is not required now. I would remove this code. I would do that main here itself. Data1 container of ptr struct some data, so the member of your choice. The ptr now becomes any address of the member. Let's say and of data b, and the member element name you should give here. That's it. Let's run. Yes, you can see that we get the same values. Now let's change this to C. You just created your own version of container of. If you see Linux source code, you see something similar, but there is a type checking as well. If you check Linux source code here, so this is something similar. You can see that they are using an offset macro here, offset off. This is a pointer what you supplied. You can see here pointer is equated to this pointer, and they are subtracting the offset. The offset they are calculating by using this offset macro. You can also use that. I will show you that. Actually, there's an offset macro in kernel.h. You just have to supply the type and member. You have to just pass in the structure type and the member. It just calculates the offset of this member by doing a zero dereferencing, what you just did in your program. So that's why you can also use here the offset of macro. Instead of this quantity, you can use offset of macro. Let me use that. What I'm going to do is I'm going to remove all these things. I just use offset of type and member. This type and member. So this actually returns a number, not pointer. It actually returns a number of long type. To include this macro, actually the standard library also gives this macro. You should include std-def.h. Whereas this macro you find in kernel.h, it is kernel's own version of offset of macro. While doing kernel programming or device driver programming, you should use this header file to get this macro. Let's run, and the result will be same, no difference. Now here this actually returns a number, right? A number quantity, not a pointer. Let's make this also a number quantity, not a pointer. I would typecast this with long. So this is now a value minus value, not pointer minus pointer. Let's run this. Now you get the same answer. Let's try with some other thing. Let's give D here, and the member element name is D. Let's try. Let's change some values here and let's try. So that's how the container of macro works, and I hope you get some idea about container of macro. The Linux container of macro, which is defined in kernel.h, also does something similar. You can see here there is a offset subtraction from the supplied pointer. But in between it does a type checking. For example, if this pointer's data type. If it doesn't match with this member's pointer data type, then it warns you saying pointer type mismatch in container of. This is actually a check. So with that note, I would like to end this lecture on container of, and I'll see you in the next lecture. The devices automatically. You need not to feed the information about the devices manually. For example, here the Wi-Fi card is connected to the PCI bus, right? So the Wi-Fi card's host bus is PCI, and the PCI has inbuilt capability to discover this Wi-Fi card automatically by accessing its configuration space, or what we call as configuration registers. You need not to write any piece of code to add the Wi-Fi card details to the kernel manually. Everything happens at the hardware level. So when the kernel detects that Wi-Fi card, for example, the kernel automatically loads the driver, which is in charge of that Wi-Fi card. And the driver configures the Wi-Fi card and it is ready to use. Same is true for USB. In USB also, so whenever you connect or remove a USB device, the information flows through the bus at the hardware level. That's how bus comes to know about what kind of hardware is connected to the USB bus. But if you consider embedded platform, the bus interfaces on the SoC or on a microcontroller is purely vendor specific. Different vendors have their own proprietary design for interconnection of devices and peripherals with a processor. There is no central bus system such as PCI to discover all on-chip as well as off-chip devices. If you take the example of simple microcontroller such as, let's say, STM32, which is based on ARM Cortex-M architecture, there is a central bus system, which is based on AHB or APB bus protocol, where various on-chip peripherals are hanging, such as GPIO controllers, I2C SPI controllers, USB controllers, etc. Through these interconnections, the processor talks to the peripherals. If you consider PIC microcontroller, it has got its own bus interfaces. If you consider some complex SoC such as AM335X from Texas Instruments, which is actually being used in our BeagleBone hardware, so they have their own interconnections and bus protocols. All these different bus interfaces of an embedded platform